Okay, hello. This is the solutions for assignment 2. So at noon on a clear summer day when the sun is directly overhead, the photons hitting the ground deliver some momentum to the ground. Because of this, a scale exposed to light from above would register a slightly larger reading than it would at night. So the actual question: estimate how much additional mass a scale would measure if it were weighing the Niagara College Welland campus on a bright, sunny day compared to at night. And I give you some given values here: area of the campus, average wavelength of solar light, average solar light intensity, and an assumed exposure of 1 second. So let's go ahead and do the calculations here. First off, I'm going to start with calculating some values for a single photon. So let's start with the momentum here. And so this is just going to be h Planck's constant over lambda, which is our 500 nanometers. I'm going to switch to the thinner pen here, because I think the thicker one is going to be a little bit messy. So I have my value for the momentum for one photon, and I'm going to do the same to find the energy of one photon. Oh, I don't actually have my value. I never finished that calculation. 1.3252 times 10 to the negative 27. Great. So now this is going to be the exact same calculation, but we are multiplying by the speed of light. And instead of writing it all out, I'm just going to write the answer here. It's 10 to the negative 19. Negative. There we go. And of course, this is joules and kilogram meters per second. So that is my momentum and my energy for a single photon. We're going to come back to that. I'm going to use those later. So now, let's find the energy of all the photons. Now, for this, we're going to take the intensity of the light, multiply by the cross-sectional area, or in this case, just the area, multiplied by the time length of the exposure. So this is going to be 1,000 for our intensity. Our given value here is 1 kilowatt per meter squared. So this is 1,000 watts per meter squared. Our area converted to meters is 250,000. And our exposure time is just 1 second. So the area of the campus is 0.25 kilometers squared. So this is not just 250. This is 250,000 because it is meters squared. It is area. Punching this all in, you get 2.5 times 10 to the 8 joules of energy. Great. Moving on. And actually, I'm going to shrink this all down a bit. Never mind. We'll worry about that later. I caught just a little too much of that with it. Moving on. Now I am going to find the number of photons, and to do that, I'm going to take the total energy and divide it by the energy of one photon. So the total energy is just going to be the number of photons multiplied by the energy of one photon. So I have rearranged this for the number of photons. So this is going to be my 2.5 times 10 to the 8 divided by my 3.9756 times 10 to the negative 19. And I'm going to get something quite large. I got I'll call this 288. Sure, I'll take a bunch of digits. 35899 times 10 to the 26. So that is the total number of photons hitting the campus every second. From here, I'm going to find the total momentum of everything. So that's going to be the number of photons multiplied by the momentum of one photon. So this is the 6 point, and actually, I'm just going to do this. So the number of photons multiplied by the momentum of one photon, which was 1.3252 times 10 to the negative 27. And this gives us about 0.83 repeated kilogram meters per second. Great. So that is our momentum. Lastly, we need to convert this momentum to mass. So using our ideas of impulse, we get that the force is equal to the momentum divided by time. So our force is just going to be the same as the momentum, but with different units because we're just dividing by 1 here. Remember, our exposure is 1 second. So we get 0.83 repeated newtons. And then using F equals ma, where A is actually just 9.8 from gravity, we get 0.83 repeated over 9.8. And we get a final mass of about 0.085 kilograms, or 85 grams. Both of these are perfectly acceptable. So that was question 1. Question 2. A gamma ray emitted from a cesium-137 source undergoes Compton scattering with a stationary electron. After scattering, the wavelength of the photon increases by 1.22 times 10 to the negative 12 meters, or just 1.22 picometers. Determine the scattering angle for the photon. Great. So this is going to use our Compton scattering formula, which I never have memorized for some reason, despite all of the times I've written it out. There we go. Now, I've chosen to write it like this without the lambda f minus lambda I, because I'm told that the wavelength of the photon increases by this amount. So that means that is delta lambda. So I don't have the initial or the final wavelength, nor do I need it. So we're looking for the scattering angle, so we are solving this for phi. So I'm going to go ahead and do that rearranging. First, I'm going to multiply everything by the mass of the electron and the speed of light. So delta lambda, MEC. There we go. Now I'm going to divide everything by H. There we go. And now I actually don't need these brackets anymore. So now I'm going to add this cosine phi to both sides, and I'm going to subtract this from both sides. So I'm going to have cosine phi equals 1 minus delta lambda MEC over H. And lastly, take the inverse cosine of both sides, 1 minus delta lambda me c over h. Great. Now, plugging in for all the constants. Our wavelength was 1.22 times 10 to the negative 12 meters. Mass of the electron, 9.11 times 10 to the negative 31 kilograms. Speed of light, 3 times 10 to the 8 meters per second. All over Planck's constant of 6.626 times 10 to the negative 34 joule seconds. And all of this punched in should get you about 60 degrees. I think it's slightly over, but round it off to the nearest degree. I believe it's 60 degrees. So that was question 2 here. I do suggest putting this equation here on your formula sheet. If you are making your own personal one, I do suggest adding that formula boxed in black on your own formula sheet, just for your own convenience. Question 3. A gamma ray emitted from a cesium-137 source undergoes Compton scattering when it is scattered off of a stationary electron. The highest energy gamma ray emitted during this decay has an energy of 662 kiloelectron volts, corresponding to a wavelength of 1.87 times 10 to the negative 12 meters. Part A, calculate the change in wavelength if the photon scatters at 0 degrees. Okay, so we are looking for delta lambda, and we have the same equation here, and I said I would switch to the thin line, but then I never actually ended up using it too much. So delta lambda equals h over me c times 1 minus the cosine of phi. Great. So let's plug in our degree and see what happens. So here we are going to have everything being the same. Oh, never mind. That little trick's not going to work for me this time. Great. And so here we see that the cosine of 0 is just equal to positive 1. So that means that this entire bracket here equals 0. And I will quickly show this, or I guess write this out. So we still have h over me c, and this is going to be 1 minus 1 so we have 0 times our constants, so therefore the change in wavelength is 0 meters. So for part A, pretty easy. No calculator required for part A. Great. For B. So this time, same question, but with 90 degrees. Let's go ahead and sub in what the cosine of 90 degrees is equal to, and that is 0. So 1 minus 0, we end up with just 1 inside here, and we end up with just h over me c as our answer. punching these constants into a calculator, we get a change in wavelength equal to 2.4 times 10 to the negative 12 meters. Great. So lastly, we have 180 degrees. And so the cosine of 180 is equal to negative 1. So this is not 0 this time. This is 1 minus negative 1. So we end up with a 2 there, actually. So this ends up being 2h over MEC. And punching that in the calculator, well, you don't even really have to. Comparing to this formula for C to the formula for part B, I think it's pretty clear to see that for part C, it's literally just 2 times your answer for part B. So this is going to be 4.8 times 10 to the negative 12 meters. It is the same, but just multiplied by 2. For part D, based on your results, explain which scatter angle transfers the greatest amount of energy to the electron and why. So, therefore, 180 degrees is the largest because it has the largest change in a lambda in wavelength. This is because the cosine function returns a negative 1 at 180 degrees, maximizing the 1 minus cosine of phi in the formula. There is no other larger number that you could possibly get using the cosine function. Clearly, 1 minus the cosine function will only grow overall if the cosine of phi is negative. So 1 minus a negative number will give you a number larger than 1. And the largest negative number that cosine can give you is negative 1. So this entire bracket, the largest number that it can ever be equal to is just 2. And that is exactly what we get at 180 degrees. So it's the largest. So that was question 3. Question 4. An electron in a particle accelerator is measured to have a momentum of 4.56 times 10 to the negative 22 kilogram meters per second. Calculate the speed of the electron using both the classical formula and the relativistic formula. Explain why the relativistic formula must be used in this case. So I'm going to do classical on the left and relativistic on the right. Momentum equals mv and momentum equals gamma mv. So there we go. There are our 2 equations here. Let's quickly do classical first. I'm going to rearrange this for velocity. So that is the other way around. P over m. So this is 4.56 times 10 to the negative 22 over 9.11 times 10 to the negative 31 kilograms. V equals 5 times 10 to the 8 meters per second. This is greater than the speed of light, c. So, not possible. That is already the reason why we need to use the relativistic formula. And so clearly the classical gives an impossible answer. It's just greater than the speed of light, so we can't use it. So this is why we need to use relativistic. Now, relativistic, we need to solve for v in this equation first before we go ahead and use it. So let's sub in what we know gamma is equal to. And we see that there's a v squared in that square root down at the bottom. So let's go ahead and get it out. I'm going to multiply both sides by everything under the square root. And at the same time, I'm going to divide everything by p. I'm going to square everything now too. So hopefully this works the way I want it to. Great. So now everything is squared. I'm going to add v squared over c squared to both sides. I'm going to factor out my v squared, sorry. I'm going to divide everything by what's in the brackets. Now I'm going to square root everything. Oops. There we go. And I'm going to redraw that square root because it's not tall enough for my liking. There we go. Okay. So, plugging in everything, we end up getting a value of 2.57 times 10 to the 8 meters per second. So this is smaller than c, the speed of light. It is allowed, so our solution does work, and this is clearly why the relativistic formula must be used for an electron with, such high momentum, or such a high speed. So this is why it must be used. Moving on. Number 5, a spaceship with a rest mass of 1,000 kilograms is accelerated to a velocity of 2.4 times 10 to the power 8 meters per second using classical physics to determine the mass of the spaceship after the acceleration. Not a trick question, try not to overthink it. In classical physics, the mass is just going to be the same. So 1,000 kilograms. We're ignoring the fact that the spaceship is going to burn a bunch of fuel and give off a bunch of fuel and lose mass because of that. Let's assume it's accelerated from some other means other than consuming fuel. So 1,000 kilograms. Part B, using relativistic physics, determine the mass of the spaceship after the acceleration. So, our solution here, there it is we are going to take a look at gamma. 1 over the square root of 1 minus v squared over c squared. There we go. And let's figure out what this gamma factor is. Let's start with this. So 1 over square root of 1 minus, our velocity was 2.4 times 10 to the 8 over 3 times 10 to the 8. And remember that these are both squared. There we go. Plugging all that in, you get about 1.667. Great. Now, our relativistic mass is just going to be equal to gamma times the regular mass. And our regular mass was just 1,000, so that's 1.667 times 1,000. So our relativistic mass is 1,667 kilograms. So there we go. I don't know what's up with me today. I cannot draw normal good boxes. Everything's just coming out as like a trapezoid. Question 6. An electron that is initially at rest is accelerated through a potential difference and reaches a de Broglie wavelength of 0.1 nanometers. How many volts must this potential difference be? 5 points. So, starting off, let's find the momentum. So, this is going to be h divided by the de Broglie wavelength. So 6.626 times 10 to the negative 34 over 0.1 times 10 to the negative 9. This is just going to give us 6.626, unsurprisingly, and times 10 to the negative 24. So really, we've just changed the exponent. Okay. Off to the side, we will leave that for now. And let's take a look at the kinetic energy for now. Great. So let's say this is our kinetic energy here. And I'm going to, just our classical formula, I'm going to multiply the right-hand side by m over m. This is the same as multiplying by 1, so I'm not actually changing anything. I'm just changing how it looks. Doing the multiplication, I get this, m squared v squared over 2m. Now I know that classical momentum is equal to mv, so I can also say that this is p squared over 2m. And, well, would you look at that? We already have the momentum. So let's plug it in. So 6.626 times 10 to the negative 24 squared over 2 times 9.11 times 10 to the negative 31. And that gives me about 2.40965 times 10 to the negative 17 joules, converting this to electron volts. I get 150. There we go. So 150 electron volts for this question. And some arrows just to make it more clear. So that was question 6. Moving on to question 7, the last question. What is the wavelength of the photon emitted when the hydrogen atom transitions from the n equals 4 to the n equals 2 energy level? I should have said when the electron in the hydrogen atom transitions from energy level to energy level. I should have specified that. My bad. Just catching that now when I'm reading it out loud. I'll adjust that for the test if I add a question like this to it. So, Part A, calculate the wavelength of the photon emitted for the n equals 4 to n equals 2 transition in a hydrogen atom. Confirm that the wavelength that you find using the Rydberg formula matches the one obtained from the hydrogen energy level formula. 2 points for each method, 4 points total. I've given both formulas here for us. So let's do the Rydberg formula first. So this is going to be 1 over lambda equals r times 1 over 2 squared minus 1 over 4 squared. And that is everything subbed in except for our Rydberg constant. I'm going to go ahead and rearrange this for lambda quickly though. And at the same time, I'm going to plug in for the Rydberg constant. There we go. And plugging all of this into a calculator gave me 485 nanometers. Nice and quick. Oops. Did not mean to move the whole question. There we go. Second method, using energy levels. So we're going to calculate for the fourth energy level first. So that's negative 13.6 electron volts over 4 squared. Punching this in my calculator, I got negative 0.85 electron volts. For the second energy level, I got negative 3.4 electron volts. And we are looking for the wavelength emitted. So for this, I'm going to need to find the change in energy level, because the change in energy level is going to be equal to the energy of the photon. So here I'm going to have negative 0.85 minus negative 3.4. And so this is going to be equal to 2.55 electron volts, the change in energy. Moving on from here, I'm going to convert that to joules. So that's going to give me 4.0851 times 10 to the negative 19 joules. And this is equal to HC over lambda. Rearranging that for lambda now, I'm going to get lambda equals HC over 4.0851 times 10 to the negative 19. Plugging in for the Planck's constant, speed of light, and punching all this in a calculator, I got 486 nanometers. Now this is a single nanometer larger than our other answer, but that's probably just due to some of the rounding I did along the way. So we have successfully answered part A here. Part B, what is the energy difference between the n equals 4 and n equals 2 energy levels in electron volts? Well, we already found that in the middle of our calculation for the energy level portion. This part B was just a relic from when this question was first written. It used to look very different. I liked this version much more, and I just ended up leaving part B down there. Just basically as a free mark for you guys, hopefully. So anyway, that was it for assignment 2. Again, if you have any questions about any of this, please either email me or ask me in class. Thanks for watching.